Okay, I'd like to talk about the quadratic formula and how it's used to solve quadratic equations. Furthermore, its proof, which is to say why it works. Okay, now given a quadratic equation, and any quadratic equation will be of the form ax squared plus bx plus c equals 0, where a, b, and c are the coefficients. And they're general coefficients because we want a general formula. Now, if you can recall the method of completing the squares, what we'll do, and essentially the proof, is to use the method of completing the squares, but using general coefficients. So the first thing to do, if you recall, is we want to create a perfect square of a binomial by ensuring that the first and second terms coincide with the expanded form of the perfect square. So the way to do that is to factor a out of the first two terms, which means to divide each of them by a. So we have x squared plus b over ax. And to leave the c as it is. Okay. And the next step now, if you recall, what we want is we want something of this form after the lowercase a. And in order to determine what the uppercase a would have to be, we expand this and see that if you use FOIL, because x plus a all squared really means x plus a times x plus a. And what we would find is that it's actually 2ax, right? Plus a squared. Okay. Now, this 2ax is going to be the b over ax, so that 2a has to be b over a, which means that the a is half of, the uppercase a is half of b over a. So a is equal to b over a divided by 2, which is, if you recall, division of fractions. We can invert and multiply. So we have b over 2a. Okay. And then a squared will be b over 2a all squared, which is square the numerator, square the denominator, and what we want to do is we want to take this fraction here and add it and subtract it right after the x. Okay. X plus c equals 0. Okay. Now, the reason we do this is that in order to complete this square, thus far we have x squared and b over ax, which are the first two terms of the quadratic trinomial, which is a perfect square. But we need the a squared term. The a squared is b squared over 4a squared. However, we cannot simply add b squared over 4a squared without changing the value of the left side in the previous line. And to maintain equality of this equation, we must essentially cancel this term at the same time as we add it. Okay, but in a sense we're uncanceling it. So the result is that we have plus b squared over 4a squared minus b squared over 4a squared squared. And therefore the value of the left side does not change and the equation remains true. Okay. Now, once we expand this out, we get squared And when we remove this term here, the last one, we actually have to multiply it by a. And the reason is as follows. Well, if we were to apply the distributive law to the entire product here, the a would be distributed over all four terms. So if you like, we can distribute the a over all four terms, but then factor again the resulting first three terms and undo the expansion, so that what we'll have is a times this trinomial minus the fourth term, which doesn't go back into the parenthetical expression, which is a times b squared over 4a squared. Okay, plus c equals 0. And just cleaning this up a little bit, we now have x. So this is the perfect square trinomial, which we wanted, which becomes x plus a all squared, and capital A was b over 2a right here. So we have x plus b over 2a squared minus a over 1 times b squared over 4a squared is cancel the a's, and we have b squared over 4a plus c equals 0. Now, in order to solve this, we need to isolate the x, and we've come a long way because we've gone from having two instances of x, which are incommensurable. Right? We cannot add x squared and x terms because they are not like terms. They are not they are not of the same order. So the next step is to isolate x, and generally speaking, when isolating a variable in an equation, the method is to unwind all of the operations which are applied to x, or whatever the variable is, in reverse order by applying the reverse operation at every stage. So what you notice is that what happens to x is that b over 2a is added to x, and then the resulting sum is squared, and then the resulting square is multiplied by a, and then to that is subtracted, or from that is subtracted b squared over 4a, and then added c. So what we need to do is we need to reverse the final operation, and that is to say to add b squared over 4a and to subtract c from both sides of the equation, so that the equation remains true. So we have a times x plus b over 2a all squared equals b squared over 4a minus c. Okay, and we can actually simplify this and combine into two fractions, right? And then the common denominator, this is c over 1, so the common denominator is 4a. So we multiply by 4a in the top and down below. So we get 4ac over 4a, which is b squared minus 4ac all over 4a. Okay, now, and just to bring this down, x plus b over 2a squared. The next step, of course, is to unwind the last operation, or the next to last operation, which is multiplication by a. And in order to do that, we multiply by 1 over a, or divide by a. Okay, and multiply by 1 over a here. Okay, and after doing so, these cancel, and we are left with simply x plus b over 2a squared equal to b squared minus 4ac over 4a squared, multiplying numerators and multiplying denominators. Okay, now the next step, I can go to another page here. I'll just write this out again. We had x plus b over 2a all squared was equal to b squared minus 4ac over 4a squared. So the next last operation is squaring. So what we want to do is we want to square root both sides. And taking the square root of the left side will actually just reverse the exponent, and we'll be left with x plus b over 2a is equal to the square root of b squared minus 4ac all over 4a squared. And just recall that when we take a square root of both sides of the equation, we need a plus or minus on one or the other side. And just a quick explanation of why that's true. If we have x squared equals 9, yes, we can take the square root of both sides. But x equals 3 is not a complete solution because x could actually also be negative 3, right? Square root of negative 3 is 9. So x plus or minus 3. Yeah, this is just a reminder. Okay, so further simplify this to by distributing the root over the numerator and denominator of the fraction. The square root of a quotient is a quotient of square roots, and this becomes plus or minus root b squared minus 4ac all over square root of 4a squared is 2a, and we have x plus b over 2a. And all that remains to be done is to subtract b over 2a from both sides, or to reverse this addition here. So we have x equals negative b over 2a plus or minus square root of b squared minus 4ac all over 2a, and collecting these two fractions into a single fraction, because we have a common denominator, we can just add the numerators. Okay, and this is the so-called quadratic formula. Right, so just for a quick application, we have the proof of the quadratic formula. It's complete, and so just as a reminder of the theorem, if ax squared plus bx plus c equals 0, and this is the general quadratic equation, then x equals negative b plus or minus square root of b squared minus 4ac all over